Good afternoon. Currently we operate with Kiwi SDRs connected to a Linux box with a spec of a Raspberry Pi 3 or above. The Pi runs ROBs via AI6VN's Whisper daemon script to decode whisper spots and estimate the noise at the same time and on the same frequencies. Spots are reported to Robinett and noise estimates to our Influx time series database. While the Kiwi and the noise estimation algorithms are well characterized, this is not always so for the RF distribution system and hardly ever for the antennas in current use. Hence, at this stage, we cannot provide absolute noise levels, hence our current focus on patterns. To make noise level estimates at the same time and frequency as receiving whisper spots, we exploit gaps in time and frequency. In time, every 2 minutes, we have a 1 second gap before whisper transmissions and an 8-second gap at the end. Here's an example of transition from whisper signals to noise at KPH. We make an RMS estimate of the noise over the quietest 50 milliseconds, usually in the post-transmit window. In frequency, there are invariably gaps between whisper signals that each occupies 6 Hz. We also listen 60 Hz either side of the whisper band. We sort the FFT amplitudes and take the total power in the lowest 30% as the noise. Our noise estimates are available to all via an Influx database and a Grafana graphical web page. Here we have noise series from when ON5KQ was comparing 2 antennas on 40 meters, a beverage in green and yellow, and a long wire in cyan and orange. However, I do remind you not to trust absolute levels. Going live to Grafana, we're looking at noise levels at KPH, Point Reyes, California, on 80 meters. And now we can add in the SDR from northern Utah. We note the differences between them, especially during daytime, where northern Utah doesn't show the troughs. We can read off individual data values, and we can save as a CSV file. Moving to patterns, here on 160 meters we have noise levels from KPH and ND7M in southern Nevada. What I can do is to shift the ND7M estimates by 2.9 dB so that, on average, the nighttime values match. The plot suggests that the daytime noise level at ND7M is raised due to local noise. The daytime troughs are flat and are 9 to 15 dB higher than at KPH. This form of plot gives us a useful method for testing for local noise, given a low noise reference station even at a distance of 1,000 kilometers. To look in more detail at coherent patterns, despite uncertainty in absolute levels, we calculate the noise level anomaly. We subtract the value for a time period from a long-term average for that same time period. Here, for KPH and the northern Utah SDR, there are times of close visual correlation, such as within the orange circle, but also times of poor or inverse correlation, as in the green circle. This is not surprising, given that the daytime noise level at northern Utah was higher somewhat than at KPH. What we have here is a non-parametric density plot of correlation coefficient on the y-axis, with local time of day, which shows low and scattered correlation during the middle of the day, but consistent and high correlation values from evening through to dawn. The previous correlation plot was at 0 lag. In this plot of correlation between northern Utah and ND7M, the correlation coefficient is denoted by color, and the y-axis shows a time shift from -120 to +120 minutes. Where they exist, the correlation peaks are mostly broad and centered on zero shift. Narrower peaks as in this snapshot, do occur, and when they are matched with short period or due to short period time fluctuations seen in this plot at KPH, Northern Utah and ND7M. We also observe seasonal noise patterns. From rural Austria, this time series spans May 2019 to last week. Time of day is on the y-axis, day of year is on the x, and colour shows the noise level. The black lines are at dawn and dusk. The daytime minimum in spring and summer may well be due to delayer absorption. More speculatively, the rise in daytime noise level in autumn into winter may be from thunderstorms in the southwest Pacific. A propagation forecast for November 2019, shown here, does suggest that propagation paths might exist. This is backed up by whisper spots at OE9GHV in Austria, where the November number of spots in light green in the afternoon are far more numerous than during June. As for questions, these are some of the ones we have.